So as mentioned before, matching is about selecting cases among those without a treatment that are as similar as possible on a set of control variables to those with the treatment, so that we can then look at the differences. So, for example, if I think gender might be a confounding factor, then I might select for each of those with the treatment as many people with the same gender without the treatment to then look at the effect. And so then the relationship between the gender and getting the treatment in the first place is cancelled out, is negated. And then I can look at the average on the outcome variable in those with the treatment and those without the treatment and look at the difference. And that is my estimator of the average treatment effect. And I will have explicitly controlled for this particular confounding factor that I used for the matching. So this is similar to calculating the average treatment effect. First, by calculating the average treatment effect for each group on the control variable or substrata. And then weigh this by the probability of being in that group in the first place. And so this way we can get an average treatment effect that controls for X, controls for being in one of those groups or substrata. Sometimes we are interested in the average treatment effect. Sometimes we narrow our interest down to the average treatment effect on the treated, in which case we are not so worried about what the impact of the treatment would have been on those who did not receive the treatment. We are only trying to estimate how big the effect of the treatment was on those who did obtain the treatment. So that reduces the question, simplifies the question a little bit. So imagine this example scenario where we have a variable y, a treatment t, and a control variable x with only two groups in x. So on the left you can see the proportions. So 36% of our sample does not have the treatment and is in category 0 on the control variable. 24% they do not have the treatment and they are in category 1, and so forth. Then in the second column you can see the proportions overall that are in each of the groups. So in control variable group category 0 there's 44% and 56% is in category 1. And then on the right you see the variables on the outcome variable. So for those without a treatment in X in control category 0, they score 20 on the dependent variable. And those with the treatment that are in this X category 0, they score 40. So you can see a clear correlation between X and Y, right? Because the 20 and 40 are much lower than 80 and 120. And you can also see a clear treatment effect. 20 and 80 are lower than 40 and 120 respectively. So how do we now calculate the average treatment effect, controlling for X? So here you see three examples. The average treatment effect using matching. So this takes into account the treatment effect, which is 40 minus 20 and 120 minus 80, weighted by the probability of being in each of these stratums in X is 0 or X is 1. So you get 0.44 times this first treatment effect, 40 minus 20, and 0.56 times this 20 treatment effect, second treatment effect, 120 minus 80. And overall you end up with 31.2 as the average treatment effect. Perhaps we are only interested in the average treatment effect on the treated. In that case, we only look at those cases where t equals 1. Yeah, so you get 8% out of 0.4 and then 32% out of 0.4. Then we end up with 36. For OLS, the equation is a little bit more complicated and therefore on the next slide. So we have of course looked at OLS in a different way, but you can reformulate it in the terminology that we have used for matching. And then you come up with this relatively complicated equation here. And we can calculate on the basis of the previous table what our OLS estimate would be. And in this case we obtain 33.5. So we can then see these as sort of weighted estimates. If we take the overall matching estimator, the last one, of the average treatment effect, then that is really the unweighted estimator, the proper average treatment effect in the population. If we look at the average treatment effect on the treated, we're looking at the average treatment effect, but we weight it by the probability of having the treatment in the first place. OLS is also an average treatment effect, but it is weighted by the variance in the treatment. So for those substrata, those groups in X that have higher variation in the treatment, they weigh more heavily in estimating the average treatment effect than those categories in X where there's very low or no variation in the treatment effect, and they will weigh very little. Yeah. So in a way, that is actually a little bit of an unnatural estimator. The matching one is a more natural way of thinking about an average treatment effect than the OLS one is. The OLS one is basically saying we will weigh those cases more heavily that contain more information about their estimate. But that is not always what we are after. So we said that in matching we will find those other cases that are similar on the cases with the treatment. So for example, we take a set of cases with treatment and then we find matching cases without treatment to put them in the sample. Or we can weigh them using these probabilities. But for that we first need to know what matching means. And if X only has two categories, it is straightforward. It's just other cases that are also 0 or also 1. But many cases, X are of course a set of variables, and there might be scale variables and categorical variables, and then you will not find an identical case which scores exactly the same on all the X variables in the sample without the treatment and the sample with the treatment. So then we are talking about distances. And so we can talk about other closely matching cases. And then there's many different ways in which one might define this distance. One can look at the Euclidean distance in this in the space defined by all the X variables. Or you can think of the covariance matrix, or you can think of explaining why and then look at which are similar in terms of coefficients and so forth. So there are many ways of defining distance here between two cases to match. In fact, one distance matrix measure is looking at the propensity score. So we defined earlier the propensity score as the predicted probability of a particular individual to obtain the treatment or not. So we can run, say, a logistic regression, which we'll discuss later in the course, and estimate the probability of any individual given X to get the treatment or not, and then use this predicted probability to match cases. So we match cases in the treatment group with other cases in the control group that have a similar propensity to obtain the treatment. And so this can help with cases where there are many control variables or they have many potential values. So it will be difficult to come up with a good measure for distance. This is one that brings all the X variables together into one coherent measure that we can look then for a close match. And so this also creates stability and addresses issues of lack of overlap, where there are simply no cases in the control group that are similar enough to the cases in the treatment group. There is some criticism on this measure though, so if you want to apply this, look carefully also for the most recent literature by Gary King. There is some serious criticism on using propensity scores for matching. So you don't want to use this uncritically. So how many to match on can also vary. So we can either do an exact matching, where we find another case in the control group that is exactly like the case we have in the treatment group. Or we can do nearest neighbor matching, where we look for one or maybe a small set, 3, 4, 5 cases in the control group that are as close as possible, the nearest to the case in the treatment group, on the basis of one of those distance measures that we discussed. This can be the propensity score or some other distance. So nearest neighbor matching means for each case in the treatment group, we find a fixed number of nearest neighbors of cases in the control group that are as close as possible, that are the closest, to the case in the treatment group. There's also something called kernel matching, where we basically match every case in the treatment group with every case in the control group, but we weigh the case based on their distance. So often we use, for example, a somewhat normal distribution, and so that we put heavy weight on the cases that are close to the treatment case, and we very much downweigh all the observations that are far from this control treatment case, but we still include them. So again, just like ridge regression versus stepwise regression, instead of including or excluding cases in our control, we just weigh them more heavily or less heavily based on how closely they are to those cases in the treatment group. So to summarize, all these methods, regression, blocking, matching, they all control for confounding factors that we can actually identify and that we can measure. So experiments are the only way of addressing confounders that we cannot observe. But once we have identified the variable as a potential confounder and we have a measure of this variable, we can apply regression, blocking or matching to address that confounding. Regression and matching are quite similar. They give similar results and the idea is the same, but they do weigh cases differently. Matching weighs cases on the basis of the control group similarity to the treatment group, either having exactly the same or some downweighting of the ones that are more different. Whereas OLS weighs the cases on the basis of the amount of variation they provide. So they weigh more heavily those cases where on the control variables where on the treatments they show the highest variation. They can be combined. You can first generate a data set using matching and then run a linear regression or other regression. This is called doubly robust and is fairly common. The choice of the algorithm, so what distance measure to use and how to select matching cases, will have significant effects on your estimates. And the research is still ongoing as to what the overall impacts are and how to make this decision, etc. And finally, propensity scores are commonly used, especially when there are many control variables, but beware that there is recent discussion here about the reliability and validity of this. So you want to be very careful.